Okay, I'll start the class. Am I audible?
Yes, ma'am. Good afternoon, ma'am.
Good afternoon. Before we start, do you have any doubts from yesterday's lecture? We had a discussion on GPS error sources and atmospheric signal propagation. So we were discussing three major error sources. First category is satellite dependent. Okay. Next category is while the signal is traveling through atmosphere from satellite to the receiver, it is going through observation medium, which through which some delay is happening. And the third category is when the signal is received at the station, some errors are induced. Okay, you might notice that for cycle slips r equals to n lambda plus phi is written. So n is the ambiguity here. That is the error. Anyone is having any doubt here? So this all these errors they make up the error budget. You can see the effects of these errors on the total delay that is happening in the signal. Total RMS is being shown as 5.3 meters. A very major portion of this error is caused by the ionosphere. So today we will see what and how ionosphere signal delay is happening. I'll slowly glide through these slides. So please let me know if you have any doubts from the previous lecture. So these are the errors induced while the GPS signal is propagating through the medium. This medium is divided into two portions, ionosphere, which is causing a delay of around 10 to 100 meters, and neutral atmosphere, or also known as troposphere, okay, which is adding 2.3 to 30 meters of delay to the geometric range. So what is geometric range? The true distance from the satellite to receiver is known as true geometric range. And what is pseudo range? This geometric range denoted by this rho symbol, as you can see in this equation, plus various delays that are happening or various errors that are happening at different places. We are adding to it so that the signal is delayed by some time. What do we mean by signal delay? We mean that the signal is received at the station after some more time than it should have been received a little bit earlier. Okay, so this amount of delay is represented in terms of distance units. Okay, how much more distance it has traveled apart from the true geometric range. That is the true distance from satellite to receiver. Okay, so this is important data that is estimated during processing when we find the accurate position coordinates of the station. You can see the division of atmosphere into two parts. Yes.
Ma'am, you said that that by delay we mean that this much of distance it has traveled more.
Yeah.
Isn't it? Ma'am, when the receiver and distance between the receiver and the satellite is constant, then ma'am, how it could have been that it would have traveled more distance?
It is like the shortest path from satellite to receiver would be direct path, okay, straight
Yes,
line.
yes,
But
yes,
since in this figure you can see, if you these red lines you can see, these are not straight lines from the satellite to the receiver. So
yes, ma'am.
naturally, some more distance has been traveled from satellite to receiver than if you make a straight line from these 2 points.
Okay,
Yes,
ma'am. Thank you.
this much more distance has been traveled more. So this is represented by the term delay. Okay, delay, when you hear the term, it means it rings something about time. Okay, but we measure the delay in terms of distance. Okay, so how much more distance has been traveled since the signal is getting delayed at the reception. Okay. The troposphere, we saw some points about troposphere, some characteristic points, that major atmospheric mass is concentrated from this 0 kilometers at the surface to 10, about 10 kilometers. Okay, and 90% of its water vapor also is here. You can see in the figure that clouds are happening in below the tropopause. Okay, so major weather is happening below the tropopause. What is tropopause? At 10 kilometers, the top boundary of the troposphere is there. How are we making distinctions between various layers of this atmosphere? We are making distinction between the layers with the vertical temperature lapse rates. Okay, what is temperature lapse? Lapse means something is decreasing. Okay, what is decreasing? Temperature is decreasing with height. Okay, so it can be the temperature can decrease with height at a constant rate or at different rates. Okay, so with different layers we have different rates of decrease of temperature. So this is known as temperature lapse rates. Okay, so wherever the temperature lapse rate is changing, we are encountering a new atmospheric layer. I hope this is clear. The major thing about troposphere in relation to GPS signal is that it is electrically neutral. Okay, what is electrically neutral? That there are no free electrons or ions, anything that can react or give some electric reaction to or give some disturbance to the GPS signal while it is propagating. Okay, no electric phenomena is happening here, no ionization is happening here. So that is why this portion below tropopause till we reach the Earth's surface, this is known as troposphere. It is electrically neutral atmosphere. Okay, it is also non-dispersive medium for radio frequency below 15 gigahertz. That means dual use of dual frequency won't help us to remove this tropospheric delay. As we will see in the ionospheric delay, that dual frequency use is beneficial. So how this whole propagation delay is originating? It is originating from the Maxwell equations, which show how electrical and magnetic field are generated and altered by each other and by the charges or currents they may encounter during the passage of through a medium. Okay, so from Maxwell equations, when we make some assumptions, we arrive at wave equations, and from wave equations, we arrive at the equation of refractive index as a function of permittivity and permeability. Okay, you can see these two equations outside the red boxes. Okay, relation between permittivity, permeability, speed of light and refractive index n. Okay, so when we talk about troposphere, we directly talk of refractive index and refractivity. Why? Since troposphere is electrically neutral, there is no some chemical reaction or electric reaction is happening. Okay, so what how the signal is being delayed because of some medium refractive index. Some amount of atmospheric refraction is happening, which is represented by the phenomena refractive index small n. Okay, small n values for atmosphere, um, uh, different types of atmosphere or different regions all over the world. These small, the values of small n will be very close to each other. Okay, because we are talking of atmospheric refraction because of the troposphere, where major portion is water vapor. Okay, that is why the main constituent that is giving us this refractive index inside the troposphere would be almost equal uh, at different regions of the world. So the value would be very little uh, difference, different from the value of 1. Okay, so that is why what we are using another term or another parameter known as refractivity instead of refractive index n. So instead of using small n, we will be using capital N in computing our tropospheric delay. Okay, why we are doing this? We are to get some different values, or so that we may distinguish slightly better than values from unity. Okay, since refractivity is a complex number, so we have a real part and imaginary part. As we discussed before, real part is responsible for refraction and this delay that is happening through the troposphere, while the imaginary part is responsible for the loss of energy. What How the energy from the signal will be lost when the signal is getting absorbed or attenuated. Okay, the signal is damping. Okay, so this phenomena is happening because of the imaginary part of the refractivity. Okay, so we have discussed how the permanent dipole moment of water is also giving some different delay characteristics, or influencing the propagation of electromagnetic waves in a different way than the other dry constituents of the air parcel. Okay, so that is why for refractivity of the troposphere, we need to understand how the dry part and the wet part is obtained. Okay, so wet and dry constituents of the atmosphere will affect the propagation delay in different ways. Why? Because water vapor is the variation and the distribution is quite different and highly varying from place to place than the dry constituents of the water, dry gases, sorry, of the atmosphere, the dry gases and everything. Okay, they are not changing much from place to place. That is why two different effects are there, propagation effects are there. Okay, that is why we are understanding this total refractivity as comprising of two different parts. Dry part caused due to dry gases or dry air, and the wet part caused due to water vapor contained inside the atmosphere. This water vapor effect can further be divided into two portions. One caused by the density of water vapor, and the other caused by the dipole component of the water vapor. So you can see these following equations. Okay. Another thing that you can see here is that H stands for hydrostatic, means hydro is not changing much. That means it represents dry. Okay, and how do we represent wet? Wet portion is represented by the term non-hydrostatic or directly wet. Okay, so you won't see D much as subscript. You will see more of H. So wherever H is the subscript, you understand that that means the dry portion of the water vapor or the delay. Okay, so generally this combination is used. Instead of using hydrostatic and non-hydrostatic, we use hydrostatic and wet. I hope this is clear. So propagation delay would naturally be the difference between two quantities. One quantity is the direct geometrical distance from satellite to receiver. This will be the shorter quantity, which is subtracted from a bigger quantity, which is the true path the signal has traveled from satellite to the receiver, undergoing the refraction and everything, bending and everything. So this distance is slightly more. So the difference between these two quantities will give us the propagation delay in distance units. Okay, so you can see delta L is capital L minus capital G. Okay, capital L value, when you substitute here, that is integral of refractive index into the distance, okay, from receiver to the satellite. So this integral is known as electrical path length. Okay, this will give us a true path, true ray path. Okay, this will be slightly larger than the geometrical distance that is given by capital G. Okay, how are we obtaining the third equation? By substituting the value of uh, refractive index with refractivity. So what was the relation? Capital N equals to n minus 1 whole brackets into 10 to the power 6. Okay, so this is how 10 to the power minus 6 is appearing here, and that minus 1 will convert to plus 1, which while integrating will give us this capital S. I hope this is a very simple math that is being used here and you understand this portion. If you have any doubt, you can ask me here. So
This
yeah.
L part one that you were saying, that electric path length. Please, can you elaborate a little bit?
Okay, electric path length is the true ray path. That the longer distance that has been traveled by the signal from satellite to receiver is given by the electric path length. Okay, wherever it is bending, wherever it is traveling a little bit more, in whichever atmospheric layer it is, okay, taking a different direction and traveling before being received at the receiver. So naturally this path is a little bit longer than the actual distance between satellite and receiver. So what is the actual distance from satellite to receiver? Capital G. Okay. What is the true ray path? Capital L. Okay. I hope this is clear. The longer path, which is that refracted and everything is being taken care of. Okay, if you see in this figure, you can see if you join from the satellite to the receiver, if you join the straight line, a straight line, that will be capital G, and this actual red line that you are seeing, it is longer than the straight line that would join these 2 points. Okay, so this is given by capital L. So capital L, this red line, minus actual distance from this point to this point is our propagation delay. I hope this is clear.
Yes, ma'am. Thank you.
This is what we are doing here. This third equation we are getting by just putting n, by using this relation, the topmost equation. So instead of small n, we want to use this capital N. What is capital N? Refractivity. What is small n? Refractive index. So I told you there are two different types of delay inside the uh, when we talk about the direction. Okay, so when the observer is looking up, the point directly above the observer is known as zenith. Okay, so the vertically straight delay will have the largest elevation angle of the satellite. Okay, elevation angle is increasing when the sun is rising, when the satellite is rising, okay, to a point directly above the observer. So for the largest elevation angle, that is 90 degrees, we have zenith delay. Okay, and when the sun or satellite is setting towards the horizon, okay, we have different elevation angles from 90 degrees to 0 degrees. Okay, so the if elevation angle of the satellite is between 0 degrees to 90 degrees, we will have slant delay. So you can see the topmost figure, this inclined line here. I hope you can see my mouse pointer. This inclined line is known as slant delay. This straight line, vertical straight line, is known as the zenith delay. Okay, so the relation between this slant delay and the zenith delay is known as mapping function. Okay, you can see here it is written, this vertically straight line is zenith delay, this inclined line is known as slant delay. Okay, this angle here is known as elevation angle of the satellite. Okay, when the satellite is here at this point, this is horizon, the satellite will rise like this, okay, towards the zenith. Okay, so when the satellite at this position, when the satellite is at this position, we have different slant delays over here. Okay, different inclined lines. All these inclined lines are the slant delays at different elevation angles from 0 degrees to 90 degrees. So if we consider many slant delays from 0 to 90 degrees, we will have so many unknowns to identify for a post, for a region. Okay, we have to find so many number of unknowns. So to reduce this problem to a finite number of unknowns, for one for each place, we can map all these slant delay for a flat homogeneous atmosphere towards the zenith direction to get zenith delay. How are we mapping this slant delay to zenith delay? By using the mapping function. So slant delay is equal to mapping function into zenith delay. We have seen this equation in further slides. We'll see. So again, what type of delays are there? If we summarize, there are two types of delay, two types of propagation delay. One is ionospheric delay, another is tropospheric delay. When we go into the tropospheric delay, we have two parts, dry and wet part. Okay, so hydrostatic delay is the dry delay and wet delay is the wet delay. We don't use non-hydrostatic term that much. We directly use wet delay. Okay, so according to which elevation angle the satellite is viewed from, we can divide these delays into two parts, slant delays or zenith delays. Okay, so what is ZHD? Zenith hydrostatic delay. What is zenith hydrostatic delay? The delay occurring due to the dry part of the troposphere when viewed, um, when the satellite is directly above the observer, okay, at the largest possible elevation angle, that is 90 degrees. So this is zenith hydrostatic delay. I hope this is clear. What is ZHD? So we are utilizing a phenomena known as hydrostatic equilibrium inside the atmosphere, okay, that gives us the relationship between gravity, pressure and density at a height. Okay. So to obtain or to empirically model ZHT, we need pressure value as an input at the at that site, as well as the location information at that site. So what is the location information? Latitude phi as well as height of the receiver. Okay. So three things we need. First is latitude, another thing is height of the receiver, and third thing is the pressure measured at that point, okay, at that receiver point. So using these three input, we can compute zenith hydrostatic delay using two very popular models. There are more models, but most popular models are Hopfield model and Sastamonen model, okay, to compute zenith hydrostatic delay. This is the equation shared which comes under the Sasta-Monin model. Talking about zenith wet delay caused by the wet portion of the refractivity inside the troposphere. Okay, this is difficult to model, so generally we do not use this empirical models for prediction of wet delay. Okay, because wet delay prediction through empirical models will be done through surface measurements of pressure and other meteorological phenomena. Okay, so as we have seen in the last lecture in the Sasta-Moinen model, what was the two inputs used to calculate ZWD? One was temperature, another was water vapor pressure. These two things have to be measured at the site. These two meteorological phenomena these values should be available with us from the surface measurements. So whatever is happening above the surface, we won't be able to capture. But major thing is happening above the surface only for water vapor. Okay, that picture won't be able these empirical models won't be able to capture this picture. Why we are able to use these empirical models successfully to find the hydrostatic delay? Because dry constituents of the atmosphere are not changing very much with height. Okay, mainly pressure is changing according to that hydrostatic equilibrium phenomena. So that is also fixed using a math equation. Okay, that model can be used to find what pressure is there at what height, and this all picture belongs to which location made by height and latitude information. Okay, so hydrostatic delay is relatively easier to model than the wet delay using empirical models. I hope this is clear. Here we are introducing a term known as precipitable water vapor, okay, or precipitable water. There are many terms depicting this phenomena: precipitable water vapor, integrated water vapor. All these things represent the same phenomena, that is the precipitated water inside a constant unit area volume um, into this column. Okay, if all the clouds are precipitating as rain inside this column of constant unit area, then the depth that of water that has been filled here will be known as the precipitable water vapor. Okay, this is the major indicator of water vapor measurements done by the signal delay measurements of GPS. Wherever you read in some papers or books anywhere that using GPS signals we are measuring the atmospheric water vapor. So how are we using? We are using this indicator, precipitable water vapor. So this precipitable water vapor can be related to zenith wet delay using a factor known as pi factor, which is a function of the temperature of that atmosphere, mean temperature of the atmosphere at that region. Okay, so we need temperature information to compute this precipitable water vapor from zenith wet delay. So you can see here zenith wet delay is not directly being computed. It is computed or calculated by using these two terms, ZTD and ZHD. Okay, so ZTD is the actual observation computed from the GPS observations. Okay, whatever the GPS instrument is measuring, this comes as a byproduct, ZTD. Okay, ZHD is modeled using empirical models like Sasta-Moine and Hoffield. Okay, and the subtraction of these two terms will yield us the ZWD. So this is how efficiently we compute ZWD rather than measuring or modeling it itself. I hope this is clear. If you have any doubts, you can ask. So the gist of this slide is that we are not modeling the ZWD portion of the total delay. What is TD? Zenith total delay. Total delay equals to dry delay plus wet delay. Okay. Dry delay or hydrostatic delay we are modeling using empirical models, and after obtaining this ZHD value we can simply subtract this value from the total delay to obtain the wet delay. Where are we getting this total delay? This we are getting as a byproduct during the GNSS processing, which is mainly done to find the correct position estimate of the station coordinates. I hope this is clear.
Ma'am, this Janet total delay contains Janet wet delay and Janet dry delay.
Yes, total delay means the total delay that is happening to the signal while traveling. Okay, now we are making it comprising of two parts because there are two parts of the atmosphere, wet part and dry part. So that is why total delay is equal to dry delay plus wet delay. So ZTD is equal to ZHD plus ZWD. We cannot model or find accurately this ZWD, so we are using a model to find ZHD. ZTD is already being obtained from the GPS observations, and subtracting these two will yield us the ZWD. ZWD will give us PWV. PWV will tell you how much or what is the variation of water vapor in the atmosphere where you are living. Okay. So mapping function. Mapping function, as I discussed, this is the relationship between zenith delay and the slant delay. Okay, so the last equation you can see, the slant total delay is equal to, the total delay means dry plus wet. So the product in the first term, ZHD into hydrostatic mapping function, this is known as slant hydrostatic delay, or you can call it SHD. SHD is obtained by multiplying mapping function to the ZHD. Similarly, the second term is the product of mapping function, wet mapping function, and the zenith wet delay. Okay, so this term is known as slant wet delay or SWD. I hope this is clear. So STD is equal to SHD plus SWD. SHD is given by ZHD into mapping function for dry part, that is MH, and SWD is given by ZWD into wet mapping function. I hope this equation is clear. This is important for the main highlight of this slide. So by taking care of the curvature effects, we can modify this simple mapping function 1 by sine elevation to continued fraction form. Okay, This continued fraction form represents the true situation because of Earth is curved, Earth's surface is curved. Okay, so when you are measuring a direction, the direction will keep changing because the base or the what you'll say, the plane surface is again getting some direction because of the curvature of the Earth. Okay, so this continued fraction can be converted to a more simpler and convenient form known as truncated continued fraction form. This form contains some coefficients A, B, and C, which depend on specific weather conditions, and they are also function of whatever location information is there. Okay, so latitude of the region, height of the place, as well as what time data you are using. Okay, what time of the year or day of the year. Okay, so the day of the year will naturally contain the weather information, what type of weather is happening over there. Okay, so these four things will tell you what are the coefficient values of A, B, C. And in this equation, the I represents hydrostatic or wet. Okay, so for wet mapping function, instead of small I, we will write W everywhere. Okay, it will give us the function value of wet mapping function. Where do we use this wet mapping function? To compute slant wet delay. How do we compute slant wet delay? Zenith wet delay into wet mapping function. How do we compute zenith wet delay? Subtracting ZHT from ZTD. Okay. Similarly, for dry or hydrostatic portion, this I is substituted with small h. Okay, so it will give us the hydrostatic mapping function or dry mapping function. There are two popular examples of mapping functions are shared here. One is Neal mapping function, another is Vienna mapping function. So Neal mapping function is a little bit fixed. The values is fixed according to the location of the site as well as the time of the year, while Vienna mapping function is more accurate, gives more accurate picture of our mapping function, as it is tracing the signal as it is changing the direction while propagating through the atmosphere. Okay, so this will give us Vienna mapping function will give us more accurate or real picture that is happening to the signal. So mapping function, I told you that you associate mapping function with elevation angle of the satellite. Okay, so in this figure, it is clear what is elevation angle and what is azimuth angle. So while considering the mapping function or while computing the mapping function, we are assuming that there is symmetry in the azimuth direction. The water vapor situation is not changing as you move from north to south, east to west. Okay, but this is not the case. Water vapor is changing as a 3D or rather 4D distribution is changing. What is 4D? Three dimensional directions plus time. Okay, so it with time the water vapor is changing in the atmosphere as well as with all the directions the water vapor is changing. So in the elevation direction, we are understanding how the water vapor is changing using mapping functions. Okay, while considering constant behavior in the azimuth direction. But to take care of the azimuth variation in the water vapor, we have to use mapping gradients. Okay, so in order to account for this kind of variation in azimuth direction, gradients need to be estimated. When are they estimated? They are estimated with the ZTD. Okay, zenith total delay of information obtained during GNSS processing. Along with it, the software also tells you what is the gradient information. What are the two types of horizontal gradients? We generally take care. One is the north-south, another is the east-west. Instead of taking all the angles, we focus on these two perpendicular directions. Okay, this is estimated using a model from Chen and Herring. It is written, the equation is given below. So mapping gradient function is function of both azimuth and elevation. While the simple mapping function used to convert slant wave delay to zenith delay is only the function of elevation angle. If you remember here, everywhere you can see sine E, mapping function E, okay, everywhere. So this E, small e is the elevation angle. So this mapping function, which is which is the relation between zenith and slant delays, is function of only the elevation of the satellite, okay, elevation angle of the satellite, while the gradients which take care of the azimuth variation of the water vapor, this gradient mapping function is function of both azimuth angle of the satellite as well as the elevation angle of the satellite. I hope this is clear. So azimuth angle is measured from the north in both directions. Okay, so you don't go from north to back to north in a complete circle. Rather, you go from north to east, north to west. Similarly, um, that's south, south to east and south to west. So this is not relevant here. Uh, so how do we treat tropospheric delay? We can completely ignore this bias by avoiding the delays caused by low elevation satellites. So as we've seen, the lower the elevation angle, that means the lower the satellite is, or the closer the satellite is towards the horizon, the longer is the delay happening. Okay, so longer delays we might not be able to ignore completely. That is why we can avoid tracking low elevation satellites. Okay, and no observations should be allowed taken below 20 degrees of elevation angle. Okay, so what is the elevation angle of zenith? Um, Zenith direction. When the satellite is at the zenith, what is the elevation angle? Can anybody answer?
Ma'am, 90 degree.
Yeah. So you understand, from 20 degrees to 90 degrees, we may use this information in computing the position accuracy. So this will not affect much. This can be ignored for most practical applications. Another way is to use an empirical model for total tropospheric delay. Okay, so as we have seen that dry part is modeled accurately while wet part is not so much. You can see error in the dry part through these models is as small as 1 centimeter, and error in the wet part is 5 centimeters. It is larger. Okay, generally these are not preferred to find the wet part of the delay. Another popular way is to directly measure this wet path of the component, okay, directly. So this can be done either using water vapor radiometer or other what you say, other instruments like this, satellite instruments, or some instruments like sun photometer, etc. We can directly measure the PWV. Okay, these instruments give us the value of precipitable water directly. So from that we can compute the zenith wet delay. But most of the times the instruments used are costly, so not viable option. So these two models we saw in the last lecture, Hopfield model. Okay, Hopfield model gives us characteristic heights. So whenever you listen to Hopfield word, you associate directly with the characteristic heights for wet troposphere and dry troposphere. It gives us expression for effective heights of the troposphere with respect to both dry and wet component of the delay. Okay, till what height wet component is prevalent and till what height the dry component is prevalent. Okay, so these two heights are obtained, and using these two heights it models the ZHD, zenith hydrostatic delay, as well as ZWD. Okay, by multiplying these characteristic heights with the corresponding portion of refractivity, we can find a zenith total delay. Okay, so these are the three equations, one for total, one for the portions, hydrostatic and wet. What is the major assumption that we have used here? One assumption is that we are assuming constant temperature lapse rate. Okay, we have seen how the temperature lapse rate is changing through various layers of the atmosphere, but here in this model we assume that it is constant. Okay, this is a shortcoming of the Hopfield model, which is taken care by the Sasta-Monin model. Okay, gravity is also not modeled here as the function of height. Okay, as we've seen in the Sasta-Monin model, we use the hydrostatic equilibrium phenomena where G is a function of height Z, as we have seen in the previous equations. This is the Sasta-Monin model. It takes only 3 input to compute hydrostatic delay. What are those 3 input? Can you tell me 3 inputs used to model the hydrostatic delay? Can anybody answer?
Ma'am, temperature, water vapor pressure.
No, hydrostatic delay. For hydrostatic delay, we only need 3 information. Hydrostatic means dry. So for dry part, we have seen in the previous slide also, where Sasta-Monin model was discussed for the first time. We are using pressure, latitude, as well as height. These 3 things we are using to find the hydrostatic delay. Okay, for the 2 things that you mentioned, it is used by Sasta-Monin model to compute the wet delay. Okay, these are the 2 inputs for wet delay, temperature as well as water vapor pressure. Okay, this model is not very popular to compute ZWD. Okay, that is why we compute ZHD from Sasta-Monin model, and we subtract this value from the ZTD to get ZWD, rather than using this equation that is mentioned here, which uses temperature at the surface as well as water vapor at the surface. So subscript S here represents at the surface. Okay. This is the total ZTD equation. Now let us come to ionosphere. Been 1 hour, so we can have a 5-minute break. All I have done so far is a quick revision about the last lecture. So if you have any doubts regarding the last lecture, you can still ask.
Ma'am, just one thing I have to clear, ma'am. Propagation delay contains 2 things, that is atmospheric delay and tropospheric delay. And tropospheric delay contains 2 things, that is dry delay and wet delay.
Yes.
Isn't it?
Yes, correct.
And ma'am, that ma'am, in tropospheric delay it comes that slant delay and zenith delay, or that in wet delay?
Wet and dry portions are a different picture. Okay, they are the picture of the components of the troposphere. Okay, so when the wet portion, that is water vapor, is influencing, we call it the wet delay, And when the dry gases like oxygen, nitrogen, and so many things are there, those affect the signal, that is known as the hydrostatic or dry delay. What you are saying, the slant and zenith, they are in relation with the position of the satellite. Okay, the
Okay.
signal is received at the receiver from any satellite. Satellite may be at the topmost vertical position, or it can be directly in front of the observer at the horizon. Okay, or any elevation angle between these two positions. Okay, so zenith and slant delays is the picture concerning the position of the satellite.
Okay, ma'am.
Okay,
Okay, ma'am.
so
Thank you.
we can have wet and dry delay for zenith and slant directions. So we can have zenith wet delay, ZWD. We can also have slant wet delay, SWD. Okay, so these two pictures you can combine and you can understand. If you have any other doubts, please ask. You may also use the chat box if you have any doubts. So I'll resume. So far we have seen the delay in the propagation of the signal caused by the troposphere. Troposphere is closer to the Earth's surface, while this ionosphere is the first layer of the atmosphere that is encountered by the signal when it comes from the satellite. Okay, so when the signal comes from the satellite, it travels through the ionosphere, then it will go through the atmosphere. So what is just a minute. Yeah, so ionosphere, as we have seen in the second or third slide, that ionosphere is subdivided into sublayers according to the electron density that is present there. So why do we call this portion of the atmosphere as ionosphere? Because some degree of ionization is happening. What is ionization? The full atom molecules are being broken down into charged particles because of some external phenomena that is influencing this portion of the atmosphere. What is that external phenomena? The ionization of these stable molecules done by the energy of the solar radiation. Okay, so for ionosphere context, you can understand these three colored bars here. Okay, first is the red bar, that is visible or infrared. Okay, another is the X-ray, that yellow bar, and that blue one is the extreme ultraviolet. Okay, so these are the three important wavelengths in the energy that is coming from the sun and interacting with this portion of the atmosphere and producing this ionized gas or ionospheric plasma. Okay. So this is generated by solar radiation, and what it is doing, it is these three wavelengths are dissociating and ionizing the neutral molecules and atoms. Okay, which energy is this? This is the energy from the solar radiation. Okay, so you can see the different lengths of these three colored bars. Okay, red is the longest, then yellow, and then this blue one. Okay, what does this mean? This means the effect where the height till which these wavelengths are affecting the atmosphere. Okay, so visible and infrared, they don't have any effect, they don't interact that much, they don't ionize any portion of the atmosphere. Okay, so these travel through the most and they are received at the receiver station. Okay, so visible and infrared from the solar radiation, they don't affect much. Okay, so they reach the Earth's surface. While X-ray and the extreme ultraviolet rays, they affect at different heights. Okay, so while interacting with the higher atmosphere, they are absorbed by these neutral molecules, and these molecules, they break into charged particles, ions. Okay, so the energy in these two wavelengths, X-rays and extreme ultraviolet rays, they are being used or utilized to produce the ionosphere. Okay, I hope this is clear. Why the visible and infrared are not affecting from the solar radiation? Because the energy in these wavelengths is rather lower to ionize properly any neutral atom or molecule that they encounter in the atmosphere. Okay, so that is why they are directly reaching at the Earth's surface. The main constituents of the upper atmosphere, that is ozone, nascent oxygen, then oxygen molecule, then nitrogen molecule, nitrogen oxide, all these things, these are the main constituents. They get ionized by the solar radiation in the wavelengths X and extreme ultraviolet, that is yellow and blue bar. Okay. And they produce the ionospheric plasma. In the topmost figure, you can see the different layers of the ionosphere. That is, capital D is the lowest layer, then capital E, then F layer. F is divided into two parts, F1 and F2. So highest electronic activity that is happening is in the F2 layer. You can see highest electron density is in the F2 layer. So highest amount of ionization that is happening among all the layers of the ionosphere is at this topmost F2 region. Okay. After F2 region, as we go even higher in the atmosphere, towards the exosphere. Exosphere means the end of the atmosphere. Okay, this electron density further decreases. Okay, this is because presence of ions and free electrons, they decrease above 1000 kilometers, and traces of free electrons are present up to altitudes of a few tens of thousands of kilometers in the plasmasphere or protonosphere. So plasmasphere and protonosphere are the parts of exosphere. Exosphere means the end of the atmosphere. Okay. So below plasmasphere is our ionosphere, and the highest possible layer where the highest electron density is encountered is the F2 region. Okay. When we talk about electron density, we means the number of free electrons per unit volume. Okay, where do we get these free electrons? We are obtaining because of the phenomena of ionization of the constituents of the atmosphere, that is these molecules, oxygen, nascent oxygen, nitrogen molecule, and nitrogen oxide, all these things. Okay, so these molecules are neutral initially, but after the absorbing the energy from X-rays and extreme ultraviolet rays, they break into ions and free electrons. Okay, so the number of free electrons per unit volume at a particular layer is the electron density contained in that layer. Okay, so this is the most important parameter which is characterizing the refractive index of the radio waves inside the ionosphere. Okay, so for troposphere, you have seen directly the term refractive index, then a new term known as refractivity. So the atmospheric refraction inside the troposphere is directly understood using the concept of refraction, using refractive index and refractivity. Okay, but here what is showing the refraction inside the ionosphere? The electron density. Okay, so electron density is used to represent the refractive index of the ionosphere. I hope this is clear. Okay, so there's a table here as well as a figure showing different layers of the ionosphere. Okay, there are two pictures inside this picture. One is the day picture, another is the night picture. Okay, so you can see different layers of ionosphere are active during the night and day. Why is that? Because the energy is coming, ionizing energy is coming from the sun. So naturally, more ionizing activity is happening during the day rather than during the night. Any residual or active layer having the residual ionization is in the E and F region. Okay, so these are the active ionized layers of ionosphere which are still active during the night time when there is no solar energy interacting with the ionosphere. Okay, that is why we are seeing two pictures, one for night and one for day. Okay, so let us discuss quickly. The lowest layer that is closest to the surface of the Earth is the D layer of the ionosphere. Okay, so height is 60 to 90 kilometers above the surface. Here, the atmosphere is relatively denser. So this is a very natural phenomena. The density decreases as we go from surface to the top of the atmosphere. Okay, so the most dense portion is the portion of the atmosphere nearest to the surface. So lowest layer, capital D, is naturally the dense atmosphere. Because of high density of atmosphere, the neutral molecules, although they are breaking up, but they are quickly recombining because their affinity towards each other is more. Why the affinity towards each other is more? Because this layer is relatively dense. Okay. The level of ionization is directly related to radiation that begins at the sunrise but again disappears at the sunset. So you can see in the night picture, we don't have a D region. We generally have E and F region. Okay, so some residual ionization may be left at local midnight but not throughout the night. Okay, for capital E layer, which is at a height of 90 to 150 kilometers, this layer is present during both day and night. Okay, naturally for day it is more active, and while in the night it doesn't disappear. The ionization doesn't disappear that much as it disappears for the D region. Okay, what do I mean by disappearing ionization? That means the atoms which have been broken into ions and electrons, they are not very quickly recombining during the night. Okay, they are still remaining separated. So this is known as ionization during the night. Now F layer is the topmost layer of the ionosphere. Okay, so during the day, this F layer separates into two portions, F1 and F2, among which F2 is the region of the highest electron density. Okay, electrons and ions, they recombine very slowly due to low pressure. Why low pressure? According to hydrostatic equilibrium inside the atmosphere, the pressure will decrease as we go with at more and more heights. Okay, so lower pressure at a larger height and higher pressure at a lower height. Okay, so because of the lower pressure of this topmost layer F, ions and electrons, they recombine very slowly. That is why observable effect of the solar radiation develops more slowly. It peaks after noon. Okay, so during the day two layers are there. During the night there is only one region, F region. Okay, there is no separation into two layers. Why there is no separation? Because there is no active ionization taking place during the night. Whatever that has happened during the day, it is still prevalent during the night. I hope this is clear. Any doubt here? You can ask.
Ma'am, that F layer, ma'am, why low pressure is there?
Low pressure is there because it is at the topmost height. With height, the pressure decreases. This is the natural phenomena in physics. Okay, so as you go upwards, the pressure will decrease. That is why low pressure.
Ma'am, that decreases, that I know, but means what is the reason behind? Is that because vapor pressure decreases or molecules of vapor decreases? Is that because of that?
I'm not very sure, but I'll check and get back to you.
Okay.
Maybe high pressure conditions will make the combining forces more active, maybe. But let me check and get back to you. Okay.
Okay.
Any other doubt here? I'll move on to the next slide. I don't know why this presenting portion is coming. Okay. So, what is the effect of the ionosphere on the signal? What is happening while the signal is traveling through this ionosphere. For major portion of undisturbed ionosphere, we can actually compensate for this error very easily. But if there is some major disturbance inside the atmosphere, known which is represented in this figure shown, that loop kind of thing that you have seen, this is um, irregular and rapid variation. Okay, this will cause irregular and rapid variation in amplitude and phase of the signal. Okay, this is known as scintillation. So this any very highly active ionosphere will lead to this phenomena known as scintillation, and this will result in errors like cycle slips, like phase measurement discontinuities, loss of logs, or position solution error. Okay, so for undisturbed ionosphere, we have a very clear reception. For a disturbed and very active ionosphere, we might get unclear picture at the ground of the signal from the satellite. Okay, so what is the effect, general effect on the propagation? It speeds up the carrier phase. So we have two observables. One is pseudo range, another is carrier phase. Pseudo range is understood using the PRN codes, CA code and PE code, as well as navigation message. Okay, so ionosphere speeds up the carrier phase measurement while it slows down the PRN codes of the GPS signal. Okay, so we will see in further slides what is phase advancement and group delay. Okay, we will see this phenomenon in further slides. For now, you understand that two different observables of GPS measurements, they are affected in two different ways by the ionosphere, not constant effect as the troposphere had. Okay. So phase advancement and group delay are manifestations of the ionosphere on the signal propagation. Scintillation can result due to diffraction of the signal while it is propagating through the ionosphere, and short-term fading and loss of strength can cause phase log problems to occur in the receiver. So these are the types of errors that can happen during the ionospheric delay. Okay. Single frequency receivers can function as long as there is not much ionospheric scintillation. As you can see the first case in the figure, the undisturbed ionosphere, there is a clear reception. Here for these cases we may use single frequency. Using single frequency receiver means just the L1 frequency we are using. Okay, not L1 and L2 both, as you are familiar with the two dual frequencies of the GPS, L1 and L2. Okay, so when there is an undisturbed ionosphere, we may still use the single frequency receivers. Okay, but for a disturbed and highly varying ionosphere, we have to use the dual frequency phenomena of the GPS so that we can cancel out this error entirely. Okay. Um, so impact on GNSS signal propagation also depends on space weather conditions. Space weather means condition within the solar system, including solar wind conditions in the magnetosphere, ionosphere, thermosphere, and exosphere. Okay, the outmost part of the atmosphere, which is interacting with the other portion of the solar system, that is known as the space weather. So whatever the space weather conditions are there, for example, solar flares, you must have heard the term solar flares, when the solar activity is very high and affecting the magnetism of celestial bodies. Okay, so all these things also affect the GNSS signal propagation. So any event happening that is measured by the satellites in the solar system will also tell you that there may be an impact on the GNSS signal propagation, and position solution can be off by as much as meters. We provide centimeter or decimeter level accuracy using GPS solutions nowadays, but position solution can be off as much as by meters. Okay, if these type of effects are not taken consideration. So let us see how the electron content is distributed inside the atmosphere. Okay, so the picture shown here on the right side, this picture represents our phenomena of atmospheric hydrostatic equilibrium, as we have discussed many times during these lectures. Okay, so what is hydrostatic balance? This air parcel is acted upon two different forces. One in the upward direction, one towards the earth. Okay, what is the upward direction force? The upward directed force due to the decrease in pressure with altitude. So this is a natural phenomena that pressure will decrease with altitude. This will cause an upward force on the air parcel. But this is balanced by the downward directed force due to gravity. Okay, so closer the air parcel to the earth's surface, more the gravity, that is natural. Okay, that is why we have dense atmosphere is dense near the surface of the earth and rarer towards the outside the atmosphere, for example, near the space. Okay, so that is why this phenomena hydrostatic balance, this governs most of the electron ionization picture as well as the pressure picture. Electron density or electron content, how it is distributed, we will see. Vertical distribution is like electron density is maximum at 200 to 400 kilometers. This is happening because of a compromise between how much solar energy that is ionizing, that is sufficient EUV and X-ray intensities is happening at a height, as well as how much dense the atmosphere there. Okay, so this is these two things are naturally the function of heights. You understood from this figure. Okay, topmost figure, at different heights these yellow and blue bars are stopping. Okay, so how much at what height, how much is the sufficient energy of these X-ray and EUV. EUV means extreme ultraviolet. Okay, these two wavelengths, how much is the sufficient energy received at what height. Okay, so naturally this is coming from the sun, so this sufficient energy will be obtained at the higher altitudes. Okay, but since according to the atmospheric hydrostatic equilibrium, density is more near the earth's surface. Okay, so sufficient density of molecules capable of being ionized is found at lower heights. So you understand there is a compromise between a higher height phenomena, that is ionization, and lower height phenomena, that is density of the atmosphere. So we have to have a compromise between these two things, and due to this compromise, we have the maximum electron content distribution at 200 to 400 kilometers. I hope I'm very clear in this first point. If you have any doubt, you can ask. So vertical distribution picture is due to the compromise between the ionizing energy coming from the sun as well as sufficient density of material that is sitting there to be ionized. Okay. These two phenomena are happening at different heights, one at higher height, one at lower height. So naturally, the compromise between these two things, these two heights, will give you the height where electron content is maximum. The parameter responsible for ionospheric delay is the total number of electrons. As we have already discussed, that refractivity of the ionosphere, refractive index of the ionosphere is represented in terms of electron content, electron density. Okay, so total number of electrons, TEC represents total electronic content. total electron content. Okay, so TEC is a function of many variables like solar ionizing flux. Flux means how much amount of that ionizing energy is being received from the from sun. That solar ionizing flux, magnetic activity, at what point of earth how much magnetism is active. Okay, what is the time of the year, season, time of the day, and what is the user location, as well as what is the viewing direction. Again, viewing direction will tell you at what direction this ionosphere is undisturbed and what direction ionosphere is active. Okay, so viewing direction will also affect this total electron content. The total electron content is assumed to be measured along the straight signal path between satellite and the receiver. That means we are ignoring the bending. What was bending? The longer signal path, the longer as well as the true signal path after being refracting and everything, that takes care of the bending also. But here, while computing the total electron content, we are assuming that the signal is not bending at all. We are measuring for the content for the straight signal path between the satellite and the receiver. Any doubt up till now? So there is a very interesting phenomena here. The integral of vertical electron density, that Ne is this symbol represents the electron density, and when we integrate it with height, we get vertical total electron content. This is just like our zenith delay, okay, in the troposphere. But here we are talking of ionosphere. We will talk in terms of VTEC. V means vertical, TEC means total electron content. Similarly, for the slant path, we will have slant total electronic content. Okay. Um, so total electron content is measured in the terms of TECU in units of TEC units. 1 TECU equals to 10 to the power 16 electrons per meter square. So you can see per meter square again gives you a picture like precipitable water vapor. Okay, but here we are not talking about water vapor at all. But this is a phenomena like water vapor, precipitable water vapor, where we were measuring the amount of water vapor inside a constant cross section. Okay, here again, just like that, inside a column of unit meter square cross section, how many electrons are there? That will give you 1 TCEU. Okay. It counts all the electrons in a columnar cylinder of unit area. This is just similar to the phenomena of precipitable water vapor. Okay, so there is one major phenomena known as Appleton anomaly. What happens is at the magnetic equator, this ionization will be very much active because of the interaction between electric and magnetic field. Okay, so what happens is these electrons and these free electrons, they are and ions, they are raised to a certain altitude above, like away from the surface of the equator, and then they interact and they fall down at either sides of the magnetic equator. Okay, so in this picture on the left side you can see magnetic equator. So this is the if you understand the ball of the earth, you are viewing as if the poles are on the sides and magnetic equator is towards the north. This kind of picture you are seeing here. Okay, so at the magnetic equator, what is happening? The electric field and horizontal magnetic field interact at the magnetic equator to raise the ionization above, okay, towards the outer of the atmosphere. from the magnetic equator to greater heights where it diffuses along the magnetic field lines. So there are, wherever there is magnetic field, there would be magnetic field lines. So these charged particles, they follow these lines to fall to latitudes of 15° north and 15° south. So north and south, you understand, at equal distances away from the equator in the north and south directions, these risen ionized particles are falling over these areas, over these latitudes on the earth. Okay, so here this is the global distribution of VTEC, that is maxima is prevalent or observed on both sides of the geomagnetic equator, which are correlated with the sun's position. Okay, um, so the largest TEC values in the world typically occur at these so-called equatorial anomaly latitudes. This is known as Appleton anomaly. We will stop here. If you want, I can show you a video, but I'm afraid you won't be able to hear the sound of the video. But anyway, you can, I hope you can read the subtitles. This will show you the picture of ionosphere. I hope the video is visible to you.
Yes, ma'am.
Yes, ma'am.
Okay.
मैम एक बार यूट्यूब वाले का वॉइस साउंड ऑन कर दीजिए.
Okay. Okay. Just a minute, I'll play it again. I hope this video was fun. It was showing very nicely what was the Appleton anomaly, that the ionized particles are rising and then falling through hoops, okay, in form of hoops and back down to the planet. At so that region where they were falling, that region was at the latitudes on the both sides of the equator, that is 15° north and 15° south. Okay. If you have any doubts up till now, you may ask and we shall end this discussion. I'll check the chat box. There are no questions here. Okay. If there are no further questions, then we shall leave the meeting.
Ma'am, can you please upload this document of yesterday's and today's class?
Yeah, I'll upload. Okay.
Thank you, ma'am.
Don't worry about it. Yeah. Okay. Okay. We'll leave then. Bye.
Thank you.
Thank you, ma'am.
Thank you.